Welcome back, chemistry fans. Now we're going to finish up the unit. Here is topic unit 7, topic 5. This is going to be something dealing with a term called hybridization. So let's jump into it right now. Hybridization is the same word that we utilize whenever we're talking about our cars, our automobiles. For a while there, we were slowly progressing towards electronic vehicles. We had hybrid vehicles, ones that used gasoline and electric at the same time. We're moving away from that. We're trying to get ourselves towards all electric vehicles, but it's taking us a while to get to that point. Hybridization in chemistry is where we combine the orbitals together. And I'll remind you what those are to make hybrid orbitals. So before we get to that, I need to define a couple of terms. One of them is resonance. Resonance is the observation that we can have multiple valid Lewis structures. You can draw it in multiple different ways. Let me show you what that means. So up here, notice that double bond. I could just as easily have drawn it at the top as I could on the left side. I could also draw it on the right side, but they wouldn't be exactly the same. So these are resonant structures. They are the exact same atoms, just rearranging where the bond is. Another example of this one, notice this molecule has 6 different structures. It has 2 double bonds, and they continue to shift around the clock where they are located. All of these are resonant structures of one another. And then finally, we get to 3 different possibilities for where this double bond could be located on this one, and how we combine them together if we wanted to draw one structure to summarize it all is this hybrid model that you see over here. And what they do is they will represent it with dotted lines. So they'll have a solid line and then a dotted line. And what that means is that those bonds are moving all around. They're not located in just one specific location. Not one of those is preferred over the other. So keeping that in mind, that's what we're talking about with hybridization. Hybridization is the combination of all of those molecules or all of those orbitals. Now, let me refresh your memory what an orbital is. We did a topic many moon ago with electron configuration called orbital notation. In orbital notation, each one of these boxes is a place where electrons can possibly be located, with a maximum of them being 2. This is for carbon. Carbon has 6 electrons. So if we were to count these, 1, 2, 3, 4, 5, 6, this would be the orbital notation for carbon. Whenever carbon gets electricity added to it, it can separate this electron and move it over to a new orbital. So that's called the excited state. Well, once that happens, now carbon can bond with 4 different atoms. So we combine all of those orbitals together. They used to be separate as S's and P's. Now we combine it together, and we call this the sp3 hybridization. S because the first one is S, and each of these are P's, and there are 3 of them, so therefore we combine them together to make it sp3. All right, so this is what we got to be able to do with our hybridization, is be able to count these. Now, the number of ligands is going to determine what your hybridization is. Notice in the examples here, I would have 2 ligands, so sp. I have 3 ligands, so spp, or you combine that together, you make that sp2. Notice next, 1, 2, 3, 4, that's 4 ligands, so that would be SPPP or sp3 if we combine them together, and then it just keeps going on. But we run out of P's, and we now have to start adding a D level, because that's how the orbitals work. You can only put 6 electrons in the P, so once we go to the next one, where we have 5, 1, 2, 3, 4, 5, we have to expand it. So it's now sp3, that's 4, and the 5th one would be D, and then finally, sp3d2 if we end up with 6 ligands. So you got to count the number of ligands to be able to figure out the hybridization. Some tricks for hybridization that you need to be aware of. Doubles and triple bonds are all 1 ligand. So keep that in mind. And if you have unshared pairs of electrons, they still count towards the ligand count. So let's do a couple of examples. I know these Lewis structures because I have worked them out before. For me, so this is a C triple bonded to an O. The O and the C both have extra electrons. So how many ligands does it have? 1, 2. So this is an sp. Now, if I go down below to HCN, it's not going to change any. Single bonded here, but triple bonded here, and I have 2 extra electrons here. Now, the hydrogen is not going to hybrid. It only has 1, so it doesn't hybridize. But the carbon, it has 1, 2 ligands, so it's sp. The nitrogen has 1, 2, so it actually has sp as well. Let's move down and let's do the CH3 NH2. Now let's take a look at the hydrogens all have single ligands, so they don't count. But the carbon has 1, 2, 3, 4. So that's SPPP, which equals sp3. The nitrogen, it also has 1, 2, 3, 4 ligands. It's also sp3. Now, if I do the last one, CH2, it's going to double bond to this N. Actually, we'll keep it as a single bond, and that way we'll get a different ligand count. All right, so now my carbon, it's going to have 1, 2, 3, 4, SPPP, that's sp3. My nitrogen is going to have 1, 2, 3, 4, SPPP, it's also sp3. Okay, so you're just counting the number of ligands, and then you assign it a hybrid orbital based on that. Next topic, last topic, is formal charge. On a formal charge, we got to figure out which one of these resonant structures is correct. Both of these are possible. I could have double bonds, or I could have a single and a triple bond. Which one is going to be more accurately reflecting what happens in nature? We have a formula to help us figure this out. So we're going to use math to figure it out. The formula is valence electrons minus unshared electrons minus the number of bonds. All right, so let's do that. Here are the rules that establish how we then evaluate our answers. Whichever answer is closest to 0 is the more probable answer. Let's jump into these. So notice, if we will, this is the these are the different resonant structures. After I do the math, notice how this structure has all zeros. This one has some positives, some negatives, and some positives. Those are not likely. This is the most likely because it has more zeros. The more zeros, the more likely you are to have a correct resonant structure. So let me now move to an example and let's work it out together. So let's do the formal charges on these structures. Let's do this last one because we can actually then do a comparison betwixt the two. And I think then this will be it for our, oh no, and then I have sigma pi bonds. All right, so let's do N double bonded and let's do an N that is triple bonded. And let's figure out which one is more likely to be the correct answer. So formal charge says you take the valence electrons. Well, for each nitrogen, they're all the same. They all have 5. Now, how many bonds does this first N have? It has 2 bonds, 1, 2. So you subtract 2. It has 4 electrons, 1, 2, 3, 4. So that means it has a charge of -1. The middle has 5 valence electrons. It has 4 bonds. It has no unshared electrons. Its charge is +1. And then the final one out there is going to be the exact same as it was on the left side. That's a -1. So I have 3 formal charges. I have -1, +1, and -1. Well, that's not close to 0. So let's see if we get better with this triple bonding, or let's see if we get worse. So I've got 5 on the left, minus a triple bond. minus 2 electrons. That's a 0. Ooh, that's already better. Let's keep going. 5 for the middle, minus 4 bonds, minus no, and that's a positive 1. Well, that didn't change. Well, let's now go to the right side. So I've got 5 minus.
Good morning. Have some construction ongoing in the Commons. So if you are not eating breakfast, please report directly to your first block class.
Okay, sorry about that disturbance there. So I've got 5 on my right nitrogen. It has 1 bond and it has 6 free electrons. So that's going to be a charge of minus 2. Ugh. All right. Now, if we were to add all of these together, they both equal up to be minus 1 overall. So we don't see a more favorable one of these two structures. However, this right here is undesirable. It's 2 away from 0. That means we're going to have more polarity on this molecule. The top molecule is only 1 charge away, either positive or negative. And I know it has a 0, but this overrides that. That is too far away. So it ends up that this is the more favorable structure. Whichever ones are generally closer to the 0 is the ones that are going to be more desirable. All right. So let's jump down now to our last terms. Coordinate covalent means that in the bond, one of the atoms is bringing all of the electrons. The other atom is not bringing any electrons to the bond. It's like going to a party and receiving gifts, but not bringing or forgetting your own gift. That's called coordinate covalent. Last topic is to understand that sigma bonds are all single bonds. That's just another term. It's a synonym. And pi bonds are the double bond and triple bonds. We're going to practice this in just a second. I want you to realize that the bonding occurs on end with the sigmas, but the pi bonds, they overlap on a vertical basis. So the bonding occurs not at the top or not in the middle. They surround the middle of the molecule. The sigmas happen in the middle. The pi's happen on the top and bottom. All right. Now let's count how many sigmas and pi's we have with this chlorine.
Good morning, bears. Our Commons is presently under construction, and there is very limited.
All right, sorry about that disturbance again. Probably will happen one more time. Let's see if we can knock it out before it happens. So I've got chlorine bonded to chlorine. It bonds as a single bond. I've got oxygen double bonded to oxygen, and I have nitrogen triple bonded to nitrogen. My goal is to identify how many sigmas and how many pi's there are in these molecules. So what you should see is that there is only 1 single bond. That means I have only 1 sigma. Now, on this oxygen, I have 1 sigma, but the second bond, it's going to end up being a pi bond. And then on the nitrogen, I have 1 sigma, but I have 2 pi bonds. This is everything that I wish to share with you. Lots of unrelated, seemingly unrelated, all talking about different details of bonds and bond energy called hybridization. Thank you so much. We'll talk with you again soon. Bye-bye.